So in the first part, we have looked at different types of membrane processes. Let us just try to quickly recap what we have done. We looked at various sizes of solutes. Then we have looked at various processes for membranes and the corresponding size range in which they are applicable. We looked at different types of membranes: isotropic, asymmetric or anisotropic, thin film composite, charged, supported liquid membranes. We looked at now little bit about transport mechanism. I asked you to find out and list factors which would affect the flow in both these cases. We will see this in detail in this part of the lecture. And we had stopped at this slide where we had tried to look at different kinds of membrane separation processes, the size range of the pores, and the kinds of membranes that are used for these processes. And I had asked you to write a homework about different types of membrane processes, what would be the driving force in each one of them, and what size of solute is being separated in each one of them. Today, what we will look at are the different mechanisms for separation of solute from the solvent or water in many cases. The first mechanism is a pressure driven pore flow mechanism. So membrane is going to be porous and the solute and the solvent is going to flow through these pores by a pressure difference across the membrane. Okay, so if you just look at the schematic of one membrane, this is an actual scanning electron microscope SEM image of the membrane. You can see that this scale is there, it is about 100 microns. So this distance, if you look at, it's about maybe about 30, 40, 50, 60 microns. And you can see that this is an asymmetric membrane. There are big pores here and there are very small pores, and there may be even an active layer deposited on top of this. So what we will try to do is we will try to look at conceptually how this membrane can be viewed in two ways. So first way is, if we look at the top cross section of the membrane, we can view this membrane as a series or as a collection of pores. So imagine each one of these is a pore and the flow is going from top to bottom, from the screen to inside. Or second way of visualizing could be that we view this membrane as a collection of particles, and gaps are formed between these particles and the liquid flows in between these gaps, again from the screen out into the screen in this particular case. So let's try to look at the first kind of concept where we are trying to visualize membrane as a collection of pores. So these pores, usually they are not straight, but if we talk about straight pore, if we assume that the pores are cylindrical, then we can visualize this as one pore and a straight cylindrical path between the feed and the permeate. So the important concept here is what is the tortuosity of the membrane, meaning if this is the membrane thickness, how much length does the solute or the solvent have to travel. So if the pore is straight, the tortuosity is 1. Suppose the pore is inclined, then the actual distance traveled is much more than the length or the thickness of the membrane. So in this particular case, if the actual distance traveled is 1.5 times the thickness of this membrane, L in this particular case, then we can say that the tortuosity is 1.5. And in reality, tortuosity can be even as large as 2.5, 3, and so on and so forth. Another concept that is important is porosity. Porosity means how much of this total area is available or is occupied by pores which is available for the flow. So for example, here pores are small d, and there are a number of pores. So if you look at this whole cross section, the total area, cross sectional area occupied by these pores, that is what is allowable for, that is what is allowed, that is where the flow can take place. So the ratio of the total available area for flow divided by the total cross section, we call this as porosity. Now pores can be small, pores can be big, or pores can be very big depending on that. So these are just some typical cases where porosity is the same, but if pore sizes are small, you will obviously see that the number of pores per unit cross sectional area is much larger as compared to a situation where the pore diameter is much bigger. Okay, so if we imagine that the membrane consists of a straight cylindrical pore, each of diameter d, can you tell me which equation would describe the flow through one such pore? And once you tell me, you can write down that equation that relates the velocity through this pore to the diameter of the pore and pressure difference. So at this point, you should pause the video and try to write the equation. Once you write, then you can continue viewing the video. So the equation that is there, that's called as Hagen-Poiseuille equation. So if you look at a cylindrical pore, the velocity through each pore is related to the delta P, and d is the diameter of the pore, mu is the viscosity of the liquid, and Lm is the thickness of the membrane. Okay, now if we go forward, now we assume that there are n number of pores per unit cross section of the membrane. Let's say epsilon is the porosity of the membrane, tau is the tortuosity of the pores, Lm is the thickness of the membrane, as we had talked about earlier. I want you to derive an equation that relates the mass flux through the membrane, mass flux meaning rate at which mass flows per unit cross sectional area, so kgs per meter square per second through the membrane. Write this equation, write an equation that relates the mass flux to the membrane properties like diameter of the pore, length Lm, length of the membrane or thickness of the membrane, porosity, number of pores per unit membrane cross section, and tortuosity. Again, at this point, you should pause the video and try to derive this equation yourself. Once you have derived this equation, then you can continue watching the video. Okay, so here we go forward. So we know that velocity is related to delta P by this Hagen-Poiseuille equation. The porosity of the membrane, if we take n number of pores per unit cross section area, pi by 4 d square would be area of one pore. So pi by 4 d square multiplied by n would be the total area available for the membrane per unit cross section. Therefore, that's nothing but the porosity. Now, mass flux through the membrane we can write in terms of rho multiplied by this velocity multiplied by this epsilon, right? So because now this is velocity is only the velocity through the pore, it is not per unit cross section of the membrane, whereas epsilon is the total porosity available area for flow divided by the total area for flow. Therefore, mass flux becomes rho multiplied by epsilon multiplied by v. Or if you want to think in terms of it, if you want to think in terms, you can also think in a different manner. Rho multiplied by velocity would be the mass flux through one such pore, and if you multiply this by pi by 4 d square, you will get into n, you will get the porosity of the membrane. So you will get rho multiplied by epsilon multiplied by v, that would be the mass flux. Now if you substitute all the values for epsilon and velocity, you can calculate pretty much what would be the flux through the membrane in terms of number of pores per unit cross section area, diameter of the pores, viscosity, tortuosity, and thickness of the membrane. Or you can also relate the number of pores to porosity. So it could be rho into epsilon into d square divided by 32 mu tau, thickness of the membrane, multiplied by delta P. Now look at each of these expressions. We can combine this term in terms of a constant related to the membrane. So for example, we can combine this part these are all properties of the membrane: number per unit area, diameter of the pore, and related to the properties of the liquid, rho and mu, and tortuosity. This number, this constant, is a particular constant for a given membrane. We can call this as permeability, or the ratio of permeability and length of the membrane we can call as permeance. So now we can write an expression like the flux is equal to permeability divided by thickness multiplied by delta P, or flux can be related to permeance multiplied by delta P. This is very much like our mass transfer or heat transfer, where we write the rate as a function of driving force and a mass transfer coefficient or a proportionality constant, or we can even think of this as flux being proportional to driving force divided by resistance of the membrane, very much like our heat and mass transfer concepts. So if you think about permeance, permeance is related to epsilon, pore diameter square, tortuosity, and length of the membrane. Of course, that rho and mu is there. It is just, I'm just writing the proportionality. These are the properties of the membrane. The rho and mu is also there, which will replace this by equality sign and the factor of 32, of course. So these properties of the membrane decide the permeance of the membrane. So for example, if the diameter of the pores is larger, permeance is larger. If porosity is larger, permeance is larger. If tortuosity is smaller, meaning more towards 1, permeance is larger. If thickness of the membrane is smaller, the permeance is larger. Now you can think about what we were talking about yesterday when we had talked about different kinds of membranes. So we talked about a symmetric membrane. So if this membrane was having this much amount of thickness, the permeance of this membrane would be very small. But replace that by an asymmetric membrane where I have a thin region which has small pores and a bigger region which acts like a support. And now you can see that the entire resistance for transfer of solvent is controlled by this region, the narrow, the small pore size region, or the thin region near the top, and therefore the overall permeance of the membrane can be higher. Let's just go back to what we were doing. Okay, so if we think in terms of SI units, in SI units, the flux we will be writing in terms of kgs per meter square per second. Delta P we would be writing in terms of Pascal. So permeability would have the units of kilogram per meter per second per Pascal, or permeance would have a units of kilogram per meter square per second per Pascal. But if you just look at this expression, J is equal to permeance into delta P. Now if you just look at this expression, you can conveniently express J and delta P in any set of convenient units, and correspondingly permeance would have those particular units. For example, it is very common to write the flux not in terms of mass flux but in terms of volumetric flux. So J could be written in terms of meter cube per meter square per second, or very commonly liters per meter square per hour, and delta P could be very commonly or conveniently written in terms of, not in terms of Pascal but in terms of bar. In that case, the permeance would have units of meter cube per meter square per hour per bar, or liters per meter square per hour bar. Let's go back to laser pointer. Yeah, so liters per meter square per hour per bar. Okay, now if we consider membrane, second option was to consider membrane as a bed of particles. Let's say a membrane is consisting of bed of particles. Each particle is of diameter dp. Voidage of the bed is epsilon. Now use Kozeny-Kármán equation and get an expression for flux. Again, at this point you should pause this video, try to derive equation yourself, and then only continue. Okay, so if we write the Kozeny-Kármán equation, delta P would be 150 mu velocity through the superficial velocity, which is same as the flux. Length of the membrane 1 minus epsilon, that's the solid fraction square, dp square, and epsilon cube. We can rearrange this in terms of velocity on the left side and everything else on the right hand side. Now mass flux we are going to write as rho multiplied by v, because this v itself is already superficial velocity across the whole membrane, because we are considering membrane as a bed of particles. So this mass flux would be rho dp square epsilon cube divided by 150 mu lm, length of thickness of the membrane, 1 minus epsilon square delta P. Now you can see that this whole term we can think in terms of permeance of the membrane, right? So you can again see that this permeance would be proportional to dp square epsilon cube thickness and 1 minus epsilon square. Of course, rho and mu and 150 are there, but these are properties of the liquid, whereas these are all properties of the membrane. So you can see that if the membrane is made up of very small particles, permeance would be smaller. If the voidage is less, permeance would be less. If the thickness is more, permeance would be less. Okay, so again, just to recap what we were talking about, asymmetric and symmetric membranes. So if membranes are asymmetric, then the thickness of the layers cannot be defined and measured precisely. So for example, this was our picture of an asymmetric membrane. So you see that there is a region where pore size is very large, there is a region where pore size is very small, but the thickness of these individual layers is not very uniform across the whole cross section, across the whole length. They are also not very well defined. There is no rigid transition between a thin region and a thin region containing small pores and a thick region containing big pores. Therefore, it is more convenient to think about membrane performance in terms of permeance rather than permeability. So that's here is what I'm trying to say. We are thinking in terms of permeance multiplied by delta P as a flux rather than permeability divided by thickness, because now this thickness, if it's an asymmetric membrane, I can't measure accurately, nor is it very well defined. Therefore, it is more convenient to think in terms of the flux as a product of permeance multiplied by pressure drop, or pressure drop divided by resistance of the membrane. So here is what we were trying to say. Flux is related to permeance multiplied by driving force delta P, or we can think of flux as driving force delta P divided by resistance. So this driving force is the pressure difference, which we call as transmembrane pressure. So transmembrane pressure means the feed side pressure minus the permeate side pressure. So again, flux can be taken in any convenient unit we want, say for example liters per meter square per hour, and transmembrane pressure can be taken in any convenient units we want, say for example bar. Then permeance would automatically take the units of flux divided by driving force. Okay, here is a problem for you to solve. Imagine a polypropylene membrane. It has a thickness of 30 micron. It has a porosity of 35%. Let's assume right now that pores are considered to be straight, cylindrical, 0.2 micron in diameter. Calculate the transmembrane pressure drop delta P required to get a pure water flux of 200 meter cube per meter square per day. Again, at this point, you should pause the video and then try to do this problem yourself before going further. Okay, here's the solution. So we looked at J was rho epsilon d square divided by 32 mu tau, thickness of the membrane delta P. So if we start using SI units, flux was 200 meter cube per meter square day. Let's convert this to SI unit now. So flux would be, if you convert the units properly, it would become 2.315 kg per meter square per second. Epsilon is 0.35, diameter is 0.2 micron, right? So 0.2 into 10 raised to minus 6 meters. Length, thickness of the membrane is 30 micron, 30 into 10 raised to minus 6 meters. So if you substitute all these things in this equation, you will get delta P as in SI units 1.59 into 10 raised to 5 Newton per meter square, or if you convert it in terms of bar, you will get 1.59 bar. If you want to think in terms of permeance now, if I want to think in terms of any units, say for example 200 meter cube per meter square day, I want to think in permeance in terms of units of liters per meter square hour. So if I want to convert this 200 meter square in meter cube into liters, I would have to take 200 multiplied by 1000. That will give me 200 multiplied by 1000 liters per meter square per day. If I want to convert to per hour, so it would be 200. It would be 200 into 1000 divided by 24. This would be the flux in terms of liters per meter square per hour. This is happening at a transmembrane pressure of 1.59 bar. So permeance would be this number divided by 1.59 bar. If you calculate it, you will get 5240 liters per meter square per hour per bar, or LMH per bar. Here is a small problem, another problem. Imagine that a manufacturer has given the following data for several of their microfiltration or ultrafiltration membranes. Each row represents one membrane type. For example, this row is for one membrane module or one membrane type, another membrane type, third membrane type, fourth membrane type, and so on and so forth. So I would like you to check the data consistency of the data using pore flow model. What I mean is, if I take 8 micron pore size, typical pore size is in this range. Number of pores per unit centimeter square is this much. Thickness of the membrane is this much. If you imagine that this data is accurate, would you get a flux of 144 gallons per minute per feet square at a transmembrane pressure of 10 pounds per square inch, considering water at 70 degrees Fahrenheit? Or take another kind of membrane, 0.2 micron pore size, 3 into 10 raised to 8 pores per centimeter square, 12 micron thickness of the membrane. If you take this membrane, would you get 3.1 gallon per minute per feet square as the water flux through the membrane at a transmembrane pressure of 10 psi? Okay, so you do this problem for yourselves. Okay, let's look at some more aspects. Sometimes the membranes that are made, they could be hydrophilic or hydrophobic. Now, so for example, and the solvent that we are trying to filter could be hydrophilic or hydrophobic. It may be liking, organics or not liking organics. So, for example, if we take water on a glass, we can think of this as a contact angle. Whereas if we take mercury on glass, we can take this as a contact angle. So, wherever contact angle is less, these are called as wettable materials. If the contact angle is more than 90, these are called as hydrophobic materials. If this is water. Now, so if the solvent is wetting the membrane very nicely, contact angles will be very small, typically zero in ideal cases. Or if the solvent is not wetting the membrane at all, this contact angle would be much greater than 1. So if you think about this capillary pressure, delta P would be 2 sigma cos theta divided by radius of the pore. Now imagine that, let's say, water is going through different membranes and there is a different contact angle between the membrane and the water. So water is not liking the membrane, or the contact angle is not 0. It has some finite value, maybe 70 degrees, maybe 80 degrees, and so on and so forth. So now if you plot flow rate versus applied pressure, you will find that unless the pressure exceeds this capillary pressure, there is practically no flow happening. That's because the capillary pressure is not permitting the water to go inside. Okay? So there is a minimum pressure at which flow rate will just start. That's called as a minimum pressure. Now if you go on increasing the pressure, you will find that the flow rate will increase in this manner. Whereas if the membrane was completely hydrophilic and you are passing water, you will just have water flow increasing linearly with pressure. Remember, flow rate increasing linearly with pressure. It is the same expression that we are talking about here. Flow rate increasing, or flux increasing linearly with pressure. So the pressure at which flow just starts, that's called as a breakthrough pressure. Now, so breakthrough pressure has to be equal to capillary pressure. So if I take a particular membrane, and a solvent, that would essentially decide the wettability. That would essentially decide the cos theta value for that particular membrane. Now I can calculate what is the pore size which is allowing the flow to go through at this breakthrough pressure. So we will find that the largest pores in the membrane we can find from the breakthrough pressure. Whereas now if you go to the other extreme, if you go on increasing pressure further and further, you come to a situation where the flow rate is linearly dependent on pressure, and that's going to tell you what is the minimum pore size in the membrane. The slope of this line is going to tell you the minimum pore size in the membrane. just a little bit about characterization of the membrane. So one of the ways to characterize is using scanning electron microscope or transmission electron microscope. You will get pictures like this. You will get photographs. You are actually photographing the membrane not visually, but using a electron. So you will get these kinds of pictures. You will be able to see the structure of the membrane. Second way to characterize the membrane is by measuring the flux versus delta P relationship. That is this relationship. So we will be able to get the breakthrough pressure, the maximum pore size. The slope here will tell us the minimum pore size. We can calculate from here, right? Or there are various ways in which we can calculate the pore size by mercury porosimetry. Again, it is depending on breakthrough pressure. Let's not get into that just now. This concept of breakthrough pressure can also be used for testing of the integrity of the membrane. So, for example, imagine that a membrane is dipped in water. Now, there is a housing which is holding the membrane that is dipped in water. Now, what we can do is we can feed nitrogen gas through the membrane from the feed side, keep the retentate closed, and note down the pressure at which bubbles of nitrogen appear on the permeate side. So the pressure at a point where bubbles appear on the permeate side, that's breakthrough pressure, right? So breakthrough pressure we can calculate, and now we can calculate the pore diameter from this breakthrough pressure. So just an example is given that you will find that in this particular case breakthrough pressure is 10 bar. So if you measure a breakthrough pressure, it gives you an idea of the pore size. Also, suppose membrane is in use for some time and you want to check whether the membrane is integrity of the membrane is proper, if the holes are developed in the membrane, you can do this membrane integrity test over maybe, let's say, after 1 month or so. If you still find that the breakthrough pressure is the same, that means you can conclude that the original membrane is retained and it has not developed any cracks or holes. Second process of diffusion through the second process of transport across the membrane is by diffusion. So when solutes are diffusing from one end of the membrane to another end of the membrane, say feed from feed to permeate, in absence of any concentration, in absence of any pressure difference, so there is no pressure induced flow, the flow is induced only because of concentration difference. We call this as dialysis to the membrane. So imagine that there is a pore like this and there are solutes on the feed side of the membrane and this is the permeate side of the membrane. So if the pore size is big, we have solutes of two different sizes. Now both these solutes can move very freely through the membrane. You will not get any separation of the solute from the solute from the small solvent. The solvent is, let's say, the small dark circles. Now if the pore size reduces, you can see that only solvent is going through and the solute is retained on the feed side. So now we will be able to get a separation between the solvent, the black, and the solute, the hollow circles. So obviously if you want the separation to happen, the molecular size must be less than the pore size. Only then you will get a separation. If molecular size is bigger, then only it will be retained by the pores. If molecular size is small, then you will have it going through the pores. So separation is possible based on different sizes. Now effective diffusivity of the solute through the membrane can be related to two parameters. One is the bulk diffusivity, that is the diffusion in absence of any medium, and a property related to what is the size of the pore as compared to the size of the solute that is going through. So that's called as a restrictive factor. So the restrictive factor is related to the size of the molecule dm and the pore size. One relationship that relates the restrictive factor to the molecular size and pore size is given by this expression. So now the effective diffusivity, we can think in terms of the product of bulk diffusivity multiplied by the restrictive factor multiplied by, of course, epsilon and tau, tortuosity of these pores. And now the flux can be related to the effective diffusivity divided by thickness of the membrane multiplied by the concentration difference, feed side and the permeate side. So we can write this diffusivity divided by thickness as permeance. So flux would be permeance multiplied by the concentration difference. And you can see if there are two different solutes, say I and J, then the restrictive factor is what is going to govern their separation. So if the bulk diffusivities are, say, Di and Dj, now the restrictive factor, if it's a big solute, the restrictive factor, so imagine that the solute is big, let's say these circles, this ratio will be closer to 1. So the restrictive factor will be closer to 0, whereas the solvent being small in size, this ratio would be small, Kr would be approximately equal to 1, and then that decides the selectivity of the solute with respect to the solvent. So here is a small problem. Consider that a membrane, there is a thickness of 5 microns, pore diameter is 9 nanometers, tortuosity is 1.5, porosity is 0.05. This membrane is used for separation of urea from beta dextrine, typical case like dialysis. So imagine that, assume that urea molecular weight is 60, beta dextrine is 1135, bulk diffusivity, obviously smaller the solute size, the bulk diffusivity is more, beta dextrine is less, having less bulk diffusivity. This is the bulk diffusivity. Molecular diameter can be calculated, you can calculate for yourself, but I am just giving you the value right now. Feed concentration and permeate concentration is here. I would like you to calculate the selectivity and flux based on pore restrictive diffusion. Again, at this point you should pause this video, calculate the numbers for yourselves based on these formulae, and then only go ahead. So the solution methodology is calculate Kr for beta dextrine, calculate Kr for urea, calculate the effective diffusivity for both the components, urea, beta dextrine, take this concentration difference and then use this formula and calculate the flux and selectivity. Okay, sometimes when we are talking about separation of gas components in the gas phase through a porous membrane, say for example we might want to separate hydrogen from carbon dioxide, which could be generated by reforming process, or hydrogen from methane. So that can be done through a membrane which has pore size which will allow hydrogen to go through but not allow methane or carbon dioxide to go through. So now diffusion of gas components or molecules through small pores is called as Knudsen diffusion. That's because the pore size is approximately same as compared to the size of the molecule. So the Knudsen diffusivity in dKi is related to the pore size and is related to the velocity of the molecules. Now again, based on kinetic theory of gases, you can calculate velocity of the molecule to temperature and molecular weight. Okay, and size of the molecule we have already calculated related to the molecular weight. Effective diffusivity. Now diffusion in such a case occurs by a combination of bulk diffusion and Knudsen diffusion. So you can think of these two processes as if they are happening in series, and so you would have bulk diffusivity and Knudsen diffusivity, and the overall diffusivity would be a reciprocal mean, geometric mean or hyperbolic mean of both these things. So now again flux can be written in terms of effective diffusivity, thickness of the membrane and concentration difference. We can write this as permeance into concentration difference. You will see that permeance is related to the effective diffusivity, which means, so if I say that the pore sizes are so small that this Knudsen diffusion is very small as compared to the bulk diffusion, then effective diffusivity is essentially controlled by the Knudsen diffusivity. So in that case, the permeance of the membrane or permeability of the membrane is related to the Knudsen diffusivity, and Knudsen diffusivity is inversely proportional to the molecular weight. So Knudsen diffusivity is inversely proportional to molecular weight. So permeance or permeability is inversely related to molecular weight. So if you have two molecules, let's say A and B types, permeability of the membrane for molecules of A type divided by permeability of the membrane to molecules of B type would just be the ratio of the molecular weight of B to molecular weight of A proportional to the square root. So for example, let's say A is hydrogen and B is methane. So hydrogen is 2, methane is 16. So the ratio of permeability of the membrane for hydrogen to methane would be molecular weight of methane divided by molecular weight of hydrogen, 16 divided by 2, that means 8, 8 raised to half, which is about slightly less than 3. That means for a particular membrane, for separating hydrogen from methane, the ratio of permeability of the hydrogen to permeability of methane, this ratio would be approximately 3. Again, here's a small problem now based on hydrogen and ethane. You can go through this, you can solve this problem. Again, it's a good idea to pause the video at this point, solve it for yourself using the formulae that we have seen, and then only continue further. Okay, so we will come to another kind of mechanism, the solution diffusion kind of mechanism, wherein the membrane is not porous, but now if a particular solute has to go through this particular membrane, then this solute has to be effectively partitioned into the membrane. These kinds of processes are important when the sizes of the solute that you are separating is so small that it is very difficult to make a porous membrane. So, for example, in gas separation or reverse osmosis or pervaporation, these kinds of membranes are used. So, in this particular case, transient cavities are formed. So, the membrane is like a bunch of polymeric chains, and transient cavities are formed through this membrane for a very small instant of time. So these pores are created for a short instant of time. They appear and they disappear. The diffusing molecule has to be partitioned from the solution phase into the membrane phase, and then only it can diffuse through the membrane. So both dissolution of the solute into the membrane and diffusion of the solute to the membrane, both these processes are important. So imagine that if I look at a position of the solute as a function of time. So at initially, let's say the solute is on one side of the membrane, let's say feed side of the membrane. So if we progress with respect to time, maybe a cavity appears that allows this solute to go inside the membrane, but for some time this cavity is the second cavity here does not appear. So the membrane, so the position of the solute essentially remains the same. When a next cavity appears, the membrane, the solute is able to jump from one location to another location, let's say going from here to here. So one way of thinking about this could be to think about the cavities that are formed which are transient in nature, and the solute jumps from one cavity to another cavity, and that's how it diffuses from one end of the membrane to another end of the membrane. Just to give you some idea about diffusivity, so if you think about molecular diffusivity, bulk diffusion of water through different media. So if you take air, water diffusivity, water vapor diffusing through air, it will have a diffusivity of about 10 raised to minus 5 meters square per second. If it is diffusing through another liquid, let's say toluene or benzene, it would have a diffusivity of something like 10 raised to minus 9 meters square per second. If you are thinking about water diffusion through a membrane, it would be significantly lower as compared to even this. So it would be about 1 into 10 raised to minus 12 meters square per second. Just to give you an idea, diffusivity of different molecules diffusing through a low density polyethylene membrane. So obviously you will expect that the smaller the size of the molecule, higher would be the diffusivity. So helium 7 into 10 raised to minus 10, hydrogen 5 into 10 raised to minus 11, nitrogen 3 into 10 raised to minus 11, propane 3 into minus 10 raised to minus 12. So diffusivity depends on the solute that is diffusing as well as the membrane that is diffusing, to which it is diffusing. Okay, so if you look at the transport mechanism, think about this as a feed and think about this as a permeate. This is the membrane. Imagine this is the concentration of the solute on the feed side there is a small mass transfer resistance Ci prime IO, that's the concentration of the solute I on the feed side of the membrane. This is getting partitioned into the membrane, it is diffusing through the membrane, and again it is getting partitioned from the membrane side to the permeate side, and again there is a mass transfer resistance from the membrane side to the bulk permeate side. Let's think about this partitioning in terms of ratios of the concentration on the feed on the membrane side divided by the feed side, or we can think in terms of the permeate side partitioning in terms of the concentration in the membrane divided by concentration in the permeate side. Now if I want to write flux through this membrane, it would be related to the diffusivity through the membrane, thickness of the membrane, and the concentration difference across the membrane, CIO minus CIL. I can replace this CIO from this expression, CIL from this expression. If I neglect the mass transfer resistance on the feed side and the permeate side, that means the bulk concentration is the same as the membrane side concentration, and the feed side and the permeate side partition coefficients, they are the same. Sometimes they are also called as sorption coefficients. Then we can rearrange this expression to get flux is equal to Ki, sorption coefficient for the solute I, diffusivity through the membrane, thickness of the membrane, concentration on the feed side minus concentration of the permeate side, and again we can think this whole term in terms of the permeance of the membrane. So flux would be related to permeance multiplied by concentration difference. Okay, let's go forward. Sometimes, especially if you are talking about separation of gas, the concentration differences are not written in terms of concentrations, but they are written in terms of partial pressures, and sorption coefficients are written in terms of solubility of the solubility of that particular gas in the membrane. So it is written in terms of the Henry's constant. Then the flux we can write in terms of Henry's constant, diffusivity, thickness of the membrane multiplied by a partial pressure difference of the solute on feed side minus the permeate side. So permeance we can think in terms of as a product of solubility, diffusivity, and thickness of the membrane. So you can see for some flux to happen, both solubility and diffusivity is going to determine the permeance of the membrane. So if we are talking about separation of two gases, not only the solubility of the gas in the membrane is important, but also diffusivity of gas in the membrane is important. So when we are talking about hydrogen and ethane or hydrogen and methane, we had only talked about the diffusivity difference. Now the flux or the selectivity of the membrane is going to be decided not just by diffusivity, but also by how much hydrogen is soluble in the membrane as compared to how much methane is soluble in the membrane, or how much hydrogen is soluble in the membrane as compared to ethane solubility in the membrane. So these are the basic mechanisms by which transport happens across the membrane. Now what we will do is we will try to apply all these principles that we have talked about to various applications like microfiltration, ultrafiltration, nanofiltration. That will be a part of the next lecture.